Let's look at graphing exponential functions. The graph of the function y equals a times b to the x power is a vertical stretch or shrink by a factor of a of the graph of the parent function y equals b to the x. So that means that the parent function is just the base, the b, raised to the x power with nothing else, just the base and the x. When I include an a in front and multiply it by b to the x, this a causes a transformation. Remember, if a is bigger than 1, it's a vertical stretch. And if a is between 0 and 1, it's a vertical shrink. If a is negative, then that means it's going to be reflected in the x-axis. Something else we can talk about is the y-intercept of the graph. The y-intercept of y equals a times b to the x is just the a value, whatever the number is in front, being multiplied by b to the x. Because imagine if I plugged in 0 into this equation for x. This would be b to the 0 power. Anything to the 0 power is just 1, and 1 times a is a. Let's look at the graphs of what our exponential functions could look like. This first example is when our base, our b, is bigger than 1. Then the numbers are going to grow very quickly. They're going to get bigger very fast, and this is called exponential growth. If our a is negative, then it causes the graph to reflect and point down. The second option is when b is between 0 and 1, or like a fraction or a decimal. That means that the numbers are going to be getting smaller very fast. This is called exponential decay. And again, if our a is negative, it causes a reflection in the x-axis and our graph will point down. Let's take a look at example 3. In example 3, we're going to graph f of x equals 4 times 2 to the x, compare the graph to the parent function, and then describe the domain and range. So our first step to make the graph is we're going to make a table. So in our table, we're going to put 0 in the middle for our x's. It's a good place to start for these types of equations. Then we'll go 2 numbers down for our x's and 2 numbers up. We're going to find the y values, or the f of x values, by taking each x, plugging them in one at a time, and filling in our table. So let's plug in negative 2. 2 to the negative second power is 1/4 times 4 is 1. 2 to the negative first power is 1/2 times 4 is 2. And then I would just keep going, keep plugging these x's in and find these y values. Do you notice the pattern for these y values? Do you notice that they're multiplying by 2 every time? And that should be the case because remember, this is an exponential function and this is how the y should react. We can also get this table of values from using our graphing calculator. Just type in this equation into y equals and then hit second table and you get these table values. Our next step is we're going to plot the points. Sorry about that. Next step, we're going to plot the points. Let's plot these points, and we're looking at this blue curve here. On the blue curve, we're plotting each of the points, and then we'll connect those points with this smooth curve, and it forms this hockey stick looking function here, exponential growth. This black function, the g of x function, that's our parent function. Remember, the parent function is this function without the a, just the b to the x power. So if I look at the difference between these two functions, the blue function is growing much faster than this black function. And that's because of the 4. The a value, remember, causes our graph to transform. So since our a is bigger than 1, that means that our graph is a vertical stretch by a factor of 4. We can also talk about the y-intercept of our graph of f, and the y-intercept would be 4. Again, it's just our a value in the equation, or look at your table when x is 0. From the graph, I can see that the domain of our function is going to be all real numbers. Our x's can be any number that we want. Doesn't matter what x is. So always for these functions, our domain is all real numbers. Our range is going to depend on the graph. Do you see how in our graph here, the numbers at the left side are getting closer and closer to 0? These numbers will never actually reach. They'll never actually reach 0. They get very close to 0, but they'll never actually reach it. And then since our graph is pointing up, our y's will get greater. So our range is y is greater than 0. Just as a hint, 0 comes because that's the number being added at the end of the function here. There's nothing being added at the end, so that's why it's 0.